We will now take a look at chapter 3 of David Albert's Time and Chance, and this chapter is called Statistical Mechanics. So in chapter 2 we looked at thermodynamics, which talks about, let's say, things like gases with certain temperatures and pressures and so on, from a macroscopic perspective. Right? It doesn't even ask the question of whether they consist of particles or how those individual particles could be behaving. It tries to understand such systems at a high level, the level of our measurement, so to speak. But statistical mechanics tries to get a maybe better or richer or truer understanding of these same systems by modeling them as large, very large collections of individual particles. And so we are going to think of a gas as consisting of many molecules, for instance, all moving, all bumping into each other, all bumping into the walls with various velocities and so on and so forth. And now, obviously, what we cannot do is calculate the trajectory of every individual particle, because there are way too many particles for us to do that. But we can use like statistical properties, such as distributions. We can talk, for instance, about the average velocity of a molecule in the gas at a certain temperature. We can talk about the distribution of velocities, like how many of them have these kinds of velocities, how many of them have those kinds of velocities. And in that way, we can build a fairly detailed model of what is going on in a thermodynamical system, but now from the perspective of this more fine-grained story of statistical mechanics. Now, when we do that, when we start thinking about a gas as consisting of, let's say, little particles, one thing that we have to do is we have to make a connection between, on the one hand, the measurements of thermodynamics, and on the other hand, those models of particles. And it's not so hard to do that. So, for instance, temperature, like the temperature of a gas or a fluid, is connected to the velocity of the particles. Higher velocity means higher temperature, lower average velocity means lower temperature. Pressure. What is pressure, this thermodynamic quantity that we can measure? Well, pressure is supposed to be the effect, or maybe it just is, the bumping into the walls of all these particles. And so if there are more particles that bump into the walls, or if those particles bump into the wall harder because they have higher velocities, then the pressure of the gas is going to be higher. And so we can connect the thermodynamic properties to the properties of the particles of the gas. But we also immediately generate some puzzles. Some puzzles that seem to suggest that maybe those thermodynamical laws, like the law of the second law of thermodynamics, the law of entropy, this idea that entropy cannot go down, that, for instance, heat can't flow from a hotter body to a colder body without anything else in the world changing, those laws might seem to be false if we think about them from the perspective of thermodynamics. And the most famous thought experiment in this regard is the thought experiment known as Maxwell's demon, named after the 19th century British physicist Maxwell, who imagined two containers of gas. One is hot, the other is cold, and they are connected by a little door. And next to that little door there is a tiny demon, and the demon is checking out these molecules. And when in the container of the hot gas a molecule is moving towards the door, and it's a very slow molecule, a molecule that is slower even than the average molecule in the cold gas, the demon quickly opens the door, and this cold molecule goes to the other side. But if, on the other hand, a very fast molecule in the cold gas, a molecule that is even faster than the average molecule in the hot gas, approaches the door, again, the demon opens the door and it lets through the fast particle. And so what happens if this demon is doing his work well is that the temperature of the colder gas is going down, and the temperature of the hotter gas is going up, and nothing else seems to be changing in the world. That would be a direct violation of the Clausius version of the second law of thermodynamics, and thereby of all the versions of the law of thermodynamics, the second law of thermodynamics. So how to deal with that thought experiment? Well, there's a large literature about Maxwell's demon that I'm not going to go into here. It's fairly interesting. Lots of people have tried to sort of tell different stories about why Maxwell's demon is impossible. But let's look at a slightly different thought experiment, one where there's no demon at all. Let's say that there's just a little door opening and closing at random. Or maybe there's just a hole, there's not even a door, right? It seems possible, like maybe not likely, but possible that some cold molecules from the hot gas will just happen to go through the hole, and some fast molecules from the cold gas will just happen to be the ones going through this little hole. And that could happen, right? Just by chance, just by accident. And then it would be actually happening that the hot gas is getting a bit hotter and the cold gas is getting a bit colder. And there just doesn't seem to be anything that makes that impossible, right? And even one molecule would, in a sense, already be enough to break the second law of thermodynamics. If one cold molecule goes from the hot gas to the cold gas, raising the average velocity of the hot gas and lowering the average velocity of the cold gas, I mean, surely that could happen. That is already a violation, a very small violation, but a violation of the second law of thermodynamics. And so the received wisdom about the second law of thermodynamics and statistical mechanics is this. It is that in statistical mechanics, it turns out that the second law, this law of entropy, doesn't hold with certainty, right? It's not the kind of law that's always true. Rather, it is a law about probabilities. It is a law that tells you that it is very improbable that heat will flow from the hotter to the colder body. It's fairly improbable that, these things will happen that lower the entropy of a system. Or in other words, it is highly probable that any system will remain at the same entropy or go to a higher entropy. And it is very improbable that any system will go to a lower entropy, but it can happen. Right? It's improbable, even maybe extremely improbable if we want a large violation of the law. But it's possible. And so the second law of statistical mechanics would seem to be only a sort of probability statement. It's a statistical law. It is something that tells you what is probable and what is improbable, not what always has to happen. So let's think a little bit more about how we can conceive of entropy and understand entropy when we think about statistical mechanics. And the crucial phrase that we have to understand in order to arrive there is the phrase phase space. So when we're talking about entropy and statistical mechanics, we always talk about phase space. Okay, so what is phase space? Well, we know about real space, right? There's this real space which is three-dimensional, and if you want to give me the position of a particle, you have to give me three numbers. Like, I can choose the axes any way I want, but let's say this is x, this is y, this is z. You've got to give me the x, y, and z coordinate, three numbers. In three-dimensional space, it locates the particle exactly. But that doesn't tell me all that there is to know about the particle. Right? Because it also has a velocity, and in order to tell me that velocity, you have to give me three more numbers. Its velocity in the x direction, its velocity in the y direction, and its velocity in the z direction. So you have to give me 6 numbers. Now that means that we could indicate the state of this particle, right? The exact state that this particle is in, by giving me a single point in a 6-dimensional space. Right? I can make a 6-dimensional space. I can think of a 6-dimensional space which has the x position, the y position, the z position, the x velocity, the y velocity, and the z velocity as its 6 axes. And then any point in that 6-dimensional space would be one state for a particle to be in. Right? It would exactly determine the position and the velocity of the particle. So it would be one state that a particle could be in. Now, suppose I have a system consisting of 2 particles. Well, if I have a system consisting of two particles, you can already see that in order to describe the entire system to me, you need to give me 12 numbers. Right? You need to give me 12 numbers. 3 for the position of the first particle, 3 for the velocity of the first particle, 3 for the position of the second particle, 3 for the velocity of the second particle, 12 numbers. And so a two-particle system, its state can be represented in a 12-dimensional space. If you give me a single point in a 12-dimensional space, that can be taken to describe the entire state of a two-particle system. And you can see where this goes, right? If you have a 1,000-particle system, you could describe its entire state by giving me one point in a 6,000-dimensional space. And if you have a billion-particle system, you could give the entire state of that by giving me one point in a 6,000,000,000-dimensional space. And that space, where just one point describes the entire system, is called a phase space. And it's very useful for scientists to talk in terms of phase spaces, make calculations in terms of phase spaces, and so on. All right, so how does this work? Well, the idea is that if we look at different states that a system could be in, and now I'm not talking about like the completely detailed micro states where you know everything, but I'm talking about sort of these big macro states, like where I measure and I find a certain temperature and a certain pressure, or I measure and I find that a particular percentage of the gas is in one half of the container, or you know, these big measurements like that. They are not one point in phase space. They are a whole area of phase space, right? All the ways that the system can be such that all the particles are in the left side of the container. Well, there's lots of ways that the system can be such that all the particles are in the left side of the container. So there's a whole part of phase space that fits that description. So we could call such a part of phase space the part of phase space that belongs to this particular macro state, right? We can identify it with this macro state. We can take, let's say it's a 1,000,000 particle system, so we have a 6,000,000 dimensional space. Well, there's one particular part of that 6,000,000 dimensional space that contains all the states of the system where all the particles are in the left side of the container. There's another part of the 6-dimensional space where that contains all the points that are all the states in which the particles are in the right side of the container. And there is yet another part of this 6-dimensional space that represents all the states where the particles are divided exactly 50-50, and so on and so forth. Right? So you can take this entire phase space and you can cut it up into parts which represents certain measurement outcomes. Now, let me make the important next point by talking with you about this pack of cards. I'm holding here a pack of cards and I'm currently shuffling it. I'm shuffling it, so I don't know exactly, what the order of this pack of cards is. It consists of exactly 26 black cards and 26 red cards. Now, suppose that I start turning over the top 26 cards. How likely is it that all of them are black? I think we will all agree that it is extremely unlikely. Let's try it out. First card, red. Well, there you have it. Already at the first card we went wrong. So that's extremely unlikely, right? After shuffling the deck, it is extremely unlikely that all the 26 top cards are black cards. On the other hand, it is far more likely that there are 13 black cards and 13 red cards among them. It's also fairly likely that it's 12 black cards and 14 red cards, or 14 black cards and 12 red cards. And it's very, very unlikely that it's 1 black card and 25 red cards, and so on and so forth. Right? So a fairly even distribution is much more likely than a very uneven distribution. And now we can ask why. Why is that the case? Is it because cards just love to mix and mingle? No, right? The cards don't care how they are shuffled. It's also not because I'm really great at shuffling the cards in such a way that black and red mix especially. It's got nothing to do with that. Here's maybe the best way to explain what's going on, or at least the standard way to explain what's going on. If you think of the number of ways that you can pick 26 cards from a deck, such that all of the cards are black, well, there's really only one way, right? You've got to pick the 26 black cards. Right? I'm just ignoring the order in which you pick them at the moment. You've got to pick the 26 black cards. There's only one way to do that. If, on the other hand, you want to pick 13 black cards and 13 red cards, there are an incredible number of ways to do that. There are, it is going to involve a lot of factorials, a lot of doing things like 26 times 25 times 24 times 23, etc., etc. It's going to be a really, really big number. So here is one way of thinking about what happens when I shuffle. When I shuffle, a completely random selection of 26 cards ends up being on top. Of all those random selections, only one consists entirely of black cards, whereas an astoundingly large number consists of 13 red cards and 13 black cards. And so if I just randomly choose one of these things by shuffling, the probability that it happens to be this one possibility that is all black is extremely low. Whereas the probability that I pick one of these many ways in which it could be 13 black and 13 red cards is fairly high. And so all I need to do really is think about how many possibilities there are, and then assume that all these possibilities are equally likely. And then I'm going to get probabilities out of it such that the outcomes that are more likely, because there are more ways to get those outcomes, the outcomes such that there are more ways to get those outcomes are more probable. I mean, that's going to be sort of the way that we have to think about this, right? So I'm very unlikely to have 26 cards on top because there's really only one way to get that. And this one way to get that is equally likely to all the many ways there are to get an even mix of red and black cards. Well, that means that, picking this exact one out of this very large collection, very low probability. So that's why we don't expect it to happen. In essence, that is the story that in statistical mechanics we tell about entropy. Take these particles moving around in this container. How many ways are there for them? Suppose that, each of them you can choose it's going to be on the left side or on the right side. How many choices can you make such that all the particles are on the left? Let's say there are 1 million particles. How many choices can you make? Well, exactly one, because for every particle you have to choose left. So there's only one way to put all of them on the left side, namely, you've got to put all of them on the left side. On the other hand, if you have 1 million particles and you need to distribute them 500,000 on the left, 500,000 on the right, there is an insane number of ways to do that. An extremely large number of ways to do that. I could have the first particle on the left and the second particle on the right and the third particle on the left and the fourth on the left and the fifth on the... but I could also do something completely different, right? there's not every sequence is good, but an astounding number of sequences are going to be good. So there are just many more ways for the system to be in an equally distributed state than there are for the system to be in this non-equally distributed state. And so on the assumption that all these states are about equally likely or exactly equally likely, on that assumption we can see that it will be extremely unlikely that we find the system in this non-equilibrium, right, where everything is on one side. And it's going to be extremely likely that we find it very, very close to an equal distribution. So let's tell the same story, but now in phase space. Take phase space, right? 1 million particles. I told you we have, let's say, a 6 million dimensional phase space. There's a part of phase space that is all the ways that the particles can be all on the left. But it's going to be a very, very small part of phase space. There's just not a lot of ways to do it. There's going to be a part of phase space where the particles are equally distributed, like half on the left, half on the right. And that is going to be a huge part of phase space because there are so many ways to do it. Now we can think of our system as kind of just wandering randomly through phase space, right? It's got these 6 million dimensional space in which it's just traveling at random. And we take a look at it at some particular moment. What is the probability that all particles are on the left? Well, this is such a tiny part of phase space that it is extremely unlikely that the system just happens to be there. Whereas this part of phase space where the particles are equally distributed is huge, and so it is very likely that the system will be found there. Right? So just that we have a kind of randomness, and we see that these parts of phase space are radically different in size, gives us a way to argue that we should expect the system to be in the kind of situation that we associate with high entropy. In fact, what Ludwig Boltzmann did when he gave a statistical mechanical definition of entropy is he just defined entropy in terms of these sizes in phase space. So the state where all the particles are on the left is a very small part of phase space, so it has a very low entropy. Whereas this state where the particles are evenly distributed over the two halves of the container, it has a very large volume in phase space, and so the entropy of that state is very, very high. Alright, so that's the basic story. And with that story, we can see that if a system happens to be in a low entropy state, like it's in this very small part of phase space, and now it's going to move through phase space, it is very likely to end up in high entropy. If it starts out in high entropy and it moves around, it's very likely to remain in high entropy. And so we seem to have an asymmetry. Right? An asymmetry where low entropy goes to high entropy and high entropy remains in high entropy. Not necessarily, but in each case with extremely high probability. Right? So with extremely high probability, low entropy goes to high entropy. With extremely high probability, high entropy goes to high entropy. And so we have an asymmetry, or at least so it seems. Now, I'm going to come back to that idea of this asymmetry in a second. I just want to say a little bit about Albert's story. I think it's the most philosophically difficult part of the chapter. Albert's story about haecceities. Because the story that I've just been telling you seems to depend on the fact that our particles are different from each other. They are distinguishable, they have their own unique identity, or as philosophers like to say, they have haecceities. Here's what I said. How many ways are there to put if you have 1 million particles, how many ways are there to put them all in the left side? I said, well, there's just one way. You put them all on the left side. How many ways are there to put these 1 million particles, half of them on the left, half of them on the right? And then I said, well, there's many ways. You could put particle 1 on the left, particle 2 on the right, or you could start the other way around. I mean, there's a huge number of ways. But that's only true if particle 1 and particle 2 are different. Like, it must make a difference that I put particle 1 here and particle 2 there, or particle 2 there and particle 1 here. If that doesn't make a difference, if all these particles are sort of identical, they don't have an identity, then, come to think of it, there is only exactly one way of putting these 1 million particles, 500,000 on the one side and 500,000 on the other side, Namely, you put 500,000 on one side and 500,000 on the other side. Right? If they don't have identities, then making changes doesn't make a difference. Right? It's still the same state. And so it seems, at first sight, that the entire story I've been telling you only works if particles have these primitive identities, these haecceities. And maybe that's not a problem. Maybe we just want to say, oh, well, particles have haecceities. Or maybe we want to say, well, thermodynamics and statistical mechanics prove that particles have haecceities. But Albert doesn't want to have none of that. Albert explains, and I think he does it very well, and I'm not going to try to repeat it without sort of diagrams. He says, look, even if you don't have haecceities, then you have to think of your phase space in a different way. It's no longer sort of a 6 million dimensional cube, because not every point in that 6 million dimensional cube is going to be another state, its own state. So you've got to actually think of that phase space in a very different way. And if you do it well, and he does it for this 2-particle system, he draws some diagrams, you can see that actually the phase space in certain parts, it shrinks much more than in other parts. And you're going to get the exact same outcomes from statistical mechanics in the cases where you have haecceities and in the cases where you don't have haecceities. And I think he's absolutely right about that. It's an important point, philosophically important point. I think he's right about that. I also think we might want to note that it doesn't really work for a pack of cards. Because the nice thing about the phase spaces that Albert is working with is that they consist of infinitely many points. And so you can sort of reduce volumes as much as you need in order to make these calculations work. And for a discrete phase space, like the one with cards, I don't think you can tell that kind of story. And so if my cards fail to have identities, if there was just one way of picking 13 black cards and 13 red cards, because all the red cards and black cards were literally the same, then you would have to tell a story, I think, not about volumes in phase space, but you would have to introduce sort of probabilities and claim that not every pick is equally probable. And you can tell that story, but it doesn't fit very nicely into this statistical mechanics stuff. So there are some limits to how we can apply these metaphors and how we have to think about probabilities and haecceities in different domains, I think. But that's not the main thing. The main thing is where we ended up with. We ended up with this idea that we have seen that if a system goes from now to the future, and it starts out in low entropy, it's very likely to go to high entropy. Because there's just so much more phase space that has high entropy. That's the definition of high entropy. And in statistical mechanics. And if we start out in the present and we go towards the future, and a system starts out in high entropy, then it is going to remain in high entropy with very high probability. And so now it seems that we have an asymmetry in time. Because as we go from the present to the future, entropy very likely goes up, and it does not very likely go down. Right? So it seems that something happens when we move towards the future, namely entropy goes up. And this is completely wrong. It is a completely wrong conclusion to draw from the story we have told, even though it is a conclusion that people draw fairly often. Well, here's a way to see how it is completely wrong. Suppose that we divide the globe, the world, like the Earth, into 2 parts. There is underneath the Eiffel Tower, and there is everywhere else. Now, if you start out underneath the Eiffel Tower, and you walk 10 miles to the front, right, in the direction you're facing, you'll end up not under the Eiffel Tower. If you start out not under the Eiffel Tower and you walk 10 miles in the direction you are facing, you will very probably remain not under the Eiffel Tower. Like, it's possible, but it's very unlikely that if you start out from like some random point in the world and walk 10 miles to the front, you end up under the Eiffel Tower. That's just extremely unlikely. So, with very high probability, if you go in the front direction from the Eiffel Tower, you end up not under the Eiffel Tower. And also with very high probability, if you go in the front direction and you start out not under the Eiffel Tower, you end up not under the Eiffel Tower. So here we have found an asymmetry in the front direction. Walking in the front direction tends to take you away from the Eiffel Tower, and it doesn't tend to take you into the Eiffel Tower. So there's an asymmetry in space. And if you want to get to the Eiffel Tower, you should walk backwards. No, right? That argument doesn't make any sense. The fact that if you walk 10 miles to your front, you'll probably end up not under the Eiffel Tower has nothing to do with the front or the back or the direction that you're walking in at all. It only has something to do with the fact that there's just a lot more not Eiffel Tower than Eiffel Tower. And that's also true when we think about entropy. The fact that if you go towards the future, you are likely to end up in a high entropy state and unlikely to end up in a low entropy state is only because there's just a lot more high entropy state than low entropy state to end up in. It has nothing to do with going towards the future. In fact, if you go towards the past, the exact same thing is true. If you're anywhere in phase space and you run the laws of nature backwards, you go back into the past, then if you are in low entropy now, you were probably in high entropy an hour ago. And if you're in high entropy now, you were probably in high entropy an hour ago, because you're just always extremely likely to be in high entropy or to end up in high entropy, whichever direction you're going in time, because there's just so much high entropy space and so little low entropy space. And so nothing that we have said so far indicates an asymmetry in time. All we have seen is that low entropy and high entropy have something to do with volume in phase space, and that if we assume that we move sort of randomly through phase space, we should always expect at the end of any evolution to be in high entropy state. We should never expect at the end of any evolution to be in a low entropy state. And if we know that we are in a low entropy state right now, it seems rational to conclude that this is a temporary, weird thing, and that we will quickly go to high entropy, and that we actually came from high entropy too. We're going to see more about this in the next couple of chapters, but this is, I think, sort of the gist of why the second law of statistical mechanics by itself in no way gives us the time asymmetry that we were looking for. So Albert does a lot of work in the later parts of this chapter to make the discussion of entropy in statistical mechanics more subtle, more correct especially. He points out that certain things that people tend to say, you either can't say them or you can't say them this easily. So one thing he points out is that I've been talking about volumes in phase space as if it's obvious what I mean by that. But it all depends on how you choose your coordinate systems. Right? I can transform coordinates in such a way that it is still completely possible to sort of use them to talk about all the physics, but the volumes in state space seem to change. So, for instance, I said, well, let's think about space as an x, a y, and a z direction, and that's possible. But you don't have to do that. You can also give any point in space by giving the distance from the origin and two angles. Right? So that would be sort of spherical coordinates. And if you do that, then, and you have like, okay, so one of my dimensions is always going to be of length 2 pi, and the other is also going to be of length 2 pi. And I mean, you're going to end up with a phase space that looks completely different, and where there can be very different volumes than in the original one. So you have to answer some fairly difficult questions about how volumes in state space even have to be calculated, and why certain ways of calculating them are okay and others are not. And nobody really knows how to do that. That's one of the things that Albert points out, and I think he's absolutely right about that. He also points out that, you know, it might just not be true in many cases that given some kind of phase space, volume in that phase space corresponds to probability in some obvious one-on-one, in some obvious one-to-one relationship. So his example is of a spatula. Like, that's something that you use in the kitchen. And he says, well, look, take houses all over the world where people own a spatula. Well, there's a gigantic phase space of where all those spatulas could be. But of course, it's not the case that every position in phase space is equally likely. Like, it's far less likely that somebody's spatula is in his bathtub than it being in the kitchen drawer. And so there could be lots of situations where there are principles that determine that probability is not equally distributed. And in fact, we know for certain that there are hard at work in our world all kinds of principles that ensure that probabilities are not equally distributed over phase space. So take all the glasses in the world that contain liquid. Well, if you look at volume in phase space, it should be overwhelmingly likely that in those glasses the temperatures are very evenly distributed, right? That there's not such a thing going on as part of the glass being liquid water at room temperature and another part of the glass being ice at something far below room temperature. That should basically never happen, a glass with liquid and ice in it. But it happens all the time. How? Yeah, because we put ice cubes into glasses, of course. Well, that's a principle, like something that's going on in the world that ensures that glasses don't actually fit. Like, glasses of liquid in the world don't actually fit what like a pure thermodynamic or statistical mechanical reflection would make you believe. And so applying statistical mechanics to the real world is going to be hard. We're going to have to answer a lot of questions that statistical mechanics by itself is not going to answer. I'm going to leave my discussion of chapter 3 at that. This video is already quite long. In the next chapter, Albert is finally going to move towards his solution for the problem of asymmetry. He's going to introduce the past hypothesis. Cosmology is gonna take a look, and then finally maybe we'll find something that actually is asymmetric in time, unlike the second law of statistical mechanics.